more wave words to talk about. I'll go ahead and list them. I'll go ahead and list them right now, and then we'll make sure we don't miss any. One thing is reflection. Another sounds similar, refraction. These words are easy to get confused because after all, we had diffraction. Now I got refraction, but there's also reflection. They're different things, so we'll try to keep them straight. So reflection, refraction, and I got another one I want to talk about. I want to talk about beats. And you know what? Related to beats, I'm going to talk about harmony. So, oh, there's another one. Resonance. Gosh, all these neat words. So we're going to talk about reflection, refraction, beats, and resonance. Well, first of all, reflection isn't too hard to talk about. You've kind of seen it. Hey, you know it means bounce, right? I could throw a ball at a wall and it would reflect off the wall. But the ball is a particle, or best thought of as a particle. And it's almost the same thing as waves bouncing. Let me show what waves might look like bouncing off something. So if I had a barrier like this, some big barrier, and there were some waves coming at it, and these are supposed to be the wave fronts. Now, this could actually be two different meanings to this picture. This could be a whole bunch of wave crests. By the way, wave front is a picture from above, or looking at the plane in which the waves are traveling, showing something like the crests or the troughs. Let's say these are wave crests. It could be a whole train of them and a snapshot of that, or if this could be a picture of successive positions, like a bunch of snapshots of it. It doesn't make much difference to the picture because either way, they're traveling perpendicular to the way they're oriented. That kind of looks right. It's the way it is. And then they bounce like that. And they bounce at the same angle away from the perpendicular that they encountered the surface at. It's almost like a pool shot. If you ever play pool, like billiards, pocket billiards, you take a shot and you're trying to do a bank shot, you kind of imagine the angle it's going to hit at. Hit it straight on, it comes straight back. Hit it at an angle like that, it skims off like that. So the waves would bounce back and go kind of like this. They might interfere with the ones coming in if there are a bunch of them. You might even get some kind of standing wave pattern. But anyway, that's reflection. One more thing about reflection I'll say is that if I send a pulse down a spring, for example, the pulse looks like that and it hits the fixed end and somebody's hanging on tight down at that end, you might recall that when it bounced back, it came back upside down. That's sort of an equal and opposite reaction thing. If somebody's holding the end very tightly and the big upward pulse comes and tries to pick their hand up, their hand is going to have to stay put. Push down is an equal and opposite reaction. So you kind of send an upside down wave back. So reflections are inverted like this if the end is fixed. However, there's such a thing as a free end. Let me give you a quick example of that. A free end might be like if you're sloshing water up against the side of the bathtub. Yeah, you can do that, splishing and splashing around. So here's the bathtub, and here's the water in the bathtub. If you send a pulse of water towards the wall of the bathtub, the side of the tub, it's going to pile up against the wall, but notice it was free to move up and down. It wasn't constrained like someone holding the end. No one's holding the water, not allowing the water to go up. So this one will actually come back right side up. There's more I could say about that, but we're in a bit of a rush. So I do want you to be aware there's reflection, which is a bouncing thing, and off a fixed end, the waves come back upside down from what they were. And if it's a free end, free to go up and down, they come back right side up. So I'll call that good for reflection. Now, here's the one, I'm going to just cross that off my list because I talked about it. And actually, I kind of want my list down low. I'm going to put my list down here. So we still have refraction we want to talk about. We still have beats, and I'll mention the harmony. I should have thought of this before. And then we'll also have this amazing thing, resonance. Yeah, we'll do all that stuff. Now let's use the top. I'll be here to do most of my writing. So, in any case, refraction. Let me do it with a little bit of a story-like thing. imagine a summer camp that's right by a swamp. And here is the swamp. And this is land. And this is land. And all week long, the camp counselors tell about this exciting thing they're going to do at the end of the summer camp. I've never been to a summer camp, so my imagination runs wild, as you can see. In any case, here on the last day of camp, they tell all the kids to go out and stand in lines. I'll show the lines of kids. They have them line up, kind of like this. These are the heads of kids. They could all be in one line, but hey, it's a big camp, so, there's like multiple lines of kids. Then they tell the kids to hold hands. So they're holding hands. Now, in a benign version of this story, they can just voluntarily hold hands, but I could also have them duct taped together. It's getting kind of creepy for summer camp. And I also would like them to close their eyes. And if you want the morbid version, you can have them blindfolded. Anyway, and then you have to scream at them to run. Maybe the whole thing is terrifying enough so they all run. This is not a very touchy-feely sort of camp, is it? Anyway, you scream at them to run, and so they all run. And which way do they run? They run forward. Now, here's the thing. What if on land they can go, I don't know, say 5 miles per hour? What if in the swamp, it's all gooey and muddy and everything, they get slowed down to 2 miles per hour? Look very closely. What happens is each kid runs into the swamp. Say this kid right here has just run to the swamp. Their little friend on the left has run just as far, and so's the friend on that left, but this kid here would have gone if they hadn't slowed down to that point. But they did slow down. So they only get like 2/5 as far, which is about here. But they're still holding hands. As this wave of kids continues to propagate into the swamp, each kid, imagine you're one of these kids. What if you are this kid? The kid on your left keeps running with you. The kid on your right just slowed down and is going to cause you to pivot. I think you can see that. I think you can see this kid right here is going to have to pivot because of this other kid running in. And of course, this continues on down the line, and I believe you can see what happens. There's sort of, I don't want to quite call it a break in the line because they're duct taped together, or they're just voluntarily holding hands really tight. But there's not a break like the line breaks apart. Instead, it's forced to suddenly bend. And not only does it bend, but since wave fronts always propagate, since waves travel perpendicular to the direction of propagation, they travel perpendicular to the orientation of the wave front. What am I saying? Anyway, it's going to change direction. In this case, it's not super dramatic, but you can definitely see it. There was a pretty big angle between this, and now the angle is smaller. Not only is the angle smaller, but the kids are closer together than they were. They're closer together because if you are running, say 10 feet behind a kid in front of you, and all of a sudden they slow down to 2/5 of your speed, they're not going to be very far ahead of you by the time you get in the swamp. They're only going to be 4 feet in front of you if you can follow my math. They're 2/5 of 10. So the wavelength is compressed. Okay, so once they've done that, they're going through the swamp slower. But look at the first kid to come out. Hey, it might be that same kid who slowed you down in the first place. That kid on your right, that kid who stepped in the mud before you did and slowed down and caused you to pivot, and then you slowed down. Hey, fair's fair. That's the same kid who emerges first on this side, right? Here you are. Here's that kid. You only make it to here when that kid gets all the way out to here. They would have only gone to here if they kept going slow, but no, they sped up. So it looks like this. So now you get this interesting thing that if these sides of the swamp are parallel to each other, they don't have to be, but if they are, you're going to actually resume your original direction and speed, and the wave fronts will look kind of the same. This again is called refraction, and I'll define it. I won't write the definition. I want you to listen to me. It's a change in the direction of wave propagation due to a change in the speed of propagation. Like, I'll say more ways. When a wave travels from one medium to another, if it's coming in anything other than head on, like hitting on at the same time, if it's in any angle at all, the angle will change. It will bend. So it's a bending or change of direction, both, in a wave and its direction of travel when it encounters a change in its speed of propagation. Why would the speed of propagation change? In this case, because you stepped in some mud, and you go slower in mud than you do on dry land. Now, in air, a change in propagation speed might be because of change in temperature. Cold air has slower moving molecules, and sound waves go slower through cold air. So we could investigate what that would do in just a moment. We'll talk about the way sound waves might refract. Now, refraction is really a neat, obvious thing with light waves. But for now, I'm just talking about kids running through a swamp. All right. Oh, let's say the camp counselors decide to follow along in their car. And this car, I don't know if this is a typical kind of car, much less one that camp counselors would have, but this one is front wheel drive. Only the front wheels provide the power to make it go. The back wheel's just along for the ride. Think what would happen if this car, Jeep, whatever it is, hits here with the front passenger side, right side tire hitting the swamp first. The tire kind of bogs down in the mud, doesn't get very far. That side of the car doesn't move very much because spinning tire. The other side, with the tire still on dry land, goes further. And if it goes further, it's going to cause the car to pivot. If you ever, maybe you've never done this, maybe you'll never have to. I hope you don't ever have to. But if you were ever like driving and you encountered a patch of ice, you might find the car pivot because of hitting the ice. Or maybe just mud. Hey, mud, it's mud. Don't slip around the ice. Anyway, so the car actually turns. Now, of course, the driver might be able to consciously steer in such a way to overcome that with some skill. But let's say they're not a very skillful driver. They're just kind of along for the ride. They don't know what they're doing. So anyway, the thing bends, and you know what? The same tire that bogged down first is the same one to get traction and grab dry land and whips that car around. So the kids think they're following them, and I guess they are, but they don't even have to try to follow them because the car kind of does it automatically. So you kind of got those mental pictures there, I hope. You can imagine the line of kids all holding hands running into the swamp. Another examples I've seen of or a marching band, marching into the swamp. Maybe that's a good one too. But the car does the same thing for roughly the same reason. Now, there's something about this that I won't dwell on too much, but it touches on a fascinating, to me, aspect of physics and of reality in general. And that is the alternative between a cause and effect brute force forced to be some way blindly, like the blindfolded kids explanation, and a purposeful, goal-oriented explanation. Now, goal-oriented explanations are no longer popular in physics. They once were. And there's a good reason they're not, because they don't bear the same fruit and have all the same mechanistic reasons for stuff. We generally in this day and age believe things happen because they get forced to, not because they want to. You remember Aristotle thinking that rocks fall because they belong with the other rocks down there? That didn't say, it sounded stupid in a way to the modern mind. And yet, you do things because you want to. Now, we're over personifying rocks, perhaps. They're just rocks. They probably don't really have dreams and aspirations and goals. But if they did, they would do something like that, wouldn't they? So it wasn't such a bad explanation in a way after all. Such an explanation, I might have said this word before, and I'm going to tell you I'm being a little bit naughty. Is that a bad word? Naughty word? It kind of is in science. Teleological explanations are ones that sometimes people throw out there because they can't deal with the more rigorous one. Let me give you a couple of examples. Like, say, in biology, you could ask the question, why do birds have wings? The obvious, quick answer is a teleological one. So they can fly. Now, you're not going to learn that in AP biology, really. I mean, you might, depending on your teacher, maybe, but the correct explanation, and I didn't put the quote marks here because I don't believe it. I'm saying it's like the standard one, is a long evolutionary one, involving like thousands or millions of generations of changes, random mutations leading to perhaps usually a not so good outcome, not adaptive thing, but some of them are positive. And then the offspring, the ones that survive inherit it. It's a natural selection thing. And natural selection takes a long time and it takes a while to explain. And it can tell you why birds have wings. But the quick and easy one is so they can fly. Got another one for you in chemistry. In chemistry, you might be asked, why does an oxygen atom bond with two hydrogen atoms to make water? And the long, correct explanation is going to actually involve stuff you can hardly do in high school, barely do in college. Quantum mechanics, you can do all this quantum mechanical stuff. You can talk about all these forces and how they behave in that realm, and it's hard and long explanation. The explanation I remember from chemistry some is because oxygen only has 6 electrons. Six. Hope I'm right. Yes, it only has 6 electrons in this outer shell thing, orbital thing, sp something. And it has neon envy. It wishes it were neon. It wishes it had 2 more electrons out there, and it would feel complete and fulfilled like the noble gases do. And so what does it do? It goes on a quest in search of something to please let it feel like it has a couple of extra electrons. And so it finds a couple of hydrogens and makes a deal. Hey, hydrogens, I'll fulfill you if you'll fulfill me. We'll pretend I've got a full outer shell, and I'll pretend you got 2 in yours. Deal. And they get together. And you know what? The explanation kind of works, even if it's kind of silly. I got one for you right here. And this one, I really like this. Okay, here's my extension of the story. Let's say that the summer camp closes down for the summer because the summer's over. And then in the fall, let's say the Army reserves come in for training, the weekend warrior kind of thing where you like once a month you go for training. My son is Marine reservist, so he knows this drill. It's literally drill. In any case, here's the same old swamp. And let's say that they're planning a march. They've only got the weekend. They're going to plan a march from point A to point B. And what they wanted, and this is still the swamp, 2 miles per hour. And this is 5 miles per hour. And this is 5 miles per hour. They're planning a march from point A to point B, and they want to do this in the least possible time. They only have the weekend. Now, the first suggestion, as they're sitting around planning the march, the first suggestion somebody makes is, well, the shortest distance between 2 points is a straight line. I propose we do that, the straight line path connecting. And, well, what do you think? Do you think that's good? And somebody says, wait a minute. Look at all this distance you're forcing our troops to walk through the swamp. How about we reduce the amount of time in the swamp? Maybe we could do this path. Maybe we could go straight down here and then over like that. I'll call that path number 2. The blue one's path number 1. And somebody says, hey, good idea. That way they won't spend much time in the swamp. But then somebody else says, I don't like that. That's ugly. It's all asymmetrical. This is so long and that's so short. And then they start evaluating this by actually using time equals distance over speed in measuring these things. I've done this before in class. There might be a meter sticking in another room. I'm not going to get it right now. I'll tell you, I've done this before in class, where we've actually measured these things and calculated the time for each segment and added them up. And I'll tell you that 2 is not the best path. There's a better one. I'll draw a better one. Maybe this path, maybe where you kind of split it like that, and that looks better, doesn't it? Now, path number 3, Now notice how you save time in the swamp by going straight through the swamp, minimizing that distance. Good idea, huh? Turns out that is better than either of the first two. But as we would see, if I were taking the time to measure everything, there's a path that's even better than that. And they keep planning and planning and planning, and finally find out that the best path is one that compromises. It hits about here, goes at an angle like that, and then down like this. And that turns out to be the best path of all, if you're real careful and mess with it and get it just the right place. And here's the weird thing about it. It turns out that the carefully planned path to minimize time turns out to be exactly what a bunch of blindfolded, duct taped together, frightened campers did by accident. Weird. Like they figured out what to do accidentally, and it's the best possible path, given that you're going to go from this point to this point. Now that, who said that? Well, in my story about the planned march, that was the deal. But it turns out it's the same path. That's always intrigued me. And there's some deep mathematical something behind this. But it does turn out that in the real world, things often do the best of all possible worlds things accidentally, blindly. Do you want to imagine that they're not really blind about it? You can if you want. I think you can mathematically just show that it's the same. But it is neat that it works that way because it gives us a tool. This is actually called Fermat's least time principle. And it does give you quick insights. You know, kind of like if you had the insight that rocks are going to try to go be with the other rocks, at least you know which way they're going to go down, even if you got the reason wrong. Kind of weird. So it's called Fermat's least time principle. I could give you more examples of it, but I won't quite yet. Instead, I want to give more examples of how this refraction thing might apply. Specifically, since this chapter was about sound, let's talk about sound for a minute. I just told you that sound goes slower in cold air because the molecules are moving slower. When they're fast, they get the message around. The little Pony Express message faster. But in cold air, they go slower. Let me show you a couple possible scenarios. You could have this be the ground, and it could be that it's hot near the ground and cold up here. That is generally the case in the daytime when the sun is hitting the ground. Now, if it's hot down here, that means things go fast. If it's cold up here, that means they go slow. I could make a definite difference between them, but you know what? I'm not even going to do that. I'm just going to say, generally speaking, if I release a wave front, like what if I'm right here and I call out, hello, because I'm trying to talk to this person way over here, far away. Look what happens. Here go my sound waves. There they go. Now look what happens. If they go faster near the ground, it's almost like the sound waves are little running weird little things like that. And their feet outrun their heads. And the waves will, since they got to go slow up here, so they go slow so that it goes far, go faster here. Do you see what's happening to the sound? The sound is curving up. The sound is curving upwards, and this person probably won't hear you very well. But maybe later that night, maybe at night, it's relatively warm up here and relatively cool near the ground at night. Now you release the sound waves, and their heads outrun their feet, and they trip over themselves. And the path of the sound is like this. Now, I haven't really messed with this or experimented with it. I have vague recollections that might correspond to what I'm talking about. Like maybe on a summer night, I might have been by a lake, and I can hear people talking on the other side of the lake, and maybe that's because the lake is cool or something. I'm not even quite sure. But I have noticed, I grew up underneath the airplanes that aren't flying much these days, but I grew up underneath the airplanes. And I noticed that in different weather conditions, the planes sounded different, louder sometimes, fainter sometimes. And I believe some of that was refraction of sound waves. So sound waves can refract, so can light waves. More on that later. I'll say we kind of took care of refraction, though we'll probably talk about it later. Next, I want to cross that off the list. It is time for beats. Beats indeed. Now, okay, I'm going to do this. There, hang on. What I'm going to do is make some little rhythm and see what you think of it. Now, I don't know if you like the rhythm particularly or not, but at least my two hands are doing the same thing. Here's something that is annoying. You know what? I just changed my mind. I'm going to use examples from your life instead of trying to do it right here on this thing. I'm just going to say some things, and you're going to try to think like, I just want to know your visceral reaction to these things. Here he goes. Your turn signal, your car, and the turn signal on the car in front of you. Your turn signal and the song on the radio. Your windshield wipers and the windshield wipers on the car in front of you. Your windshield wipers and your turn signal. Your windshield wipers or turn signal and the song on the radio. The song on the radio and the sound of your footsteps on the treadmill as you run. Now, I've got to let somebody in. Hang on just a second. I'm back. Okay, so I don't know if any of those things made you go, ugh, or not, but if they did, here's why. Because sometimes your turn signal's flashing and you're seeing the nice regular flash of the turn signal, and the person in the car in front of you, also waiting to turn left at the red light or whatever it is, has their turn signal on, and at first you go, whoa, look, they're going together. But then you notice they're not quite together. Instead of blink, 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 they're kind of going blink, 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 blink. Uh-oh. And they're really irritating for a moment. And then you kind of happy for just a second as they're opposite. But then they mess that up, and they get together again. Then they get messed up again. Then they get together again. That's because two slightly different frequencies can't stay together all the time. Your windshield wipers and the song on the radio. Whatever your song you like to listen to is. It's kind of neat there for just a moment until you realize the synchrony is not perfect and they get out of sync. Oh, swinging on a swing set. When I was a kid, it used to be that like you're swinging on a swing set with somebody. If you're swinging with them, they say, you're married, whatever. And if it does like this, I guess you're divorced, I suppose. But anyway, look, you're going together, so you're married. But what if one of you starts to get ahead of the other one? The feeling is sort of annoying. Like you either want to be in sync with them or opposite, because that's kind of neat too. The really annoying things when they're a little different. What I'm going to do is I'm going to make some sounds that do what I'm talking about here. Okay, like here's my hands going together. Pretty much. Now listen to them not go together. I'm not sure I did that very well. Sometimes they're not going together, but you still think it's neat, like this. There are some ratios of frequencies that kind of make people happy, and others are just really irritating. So let me explain this by drawing a picture of a sound wave, or at least sound waves are longitudinal, hard to draw. But anyway, look, here's one wave, and that's a blue wave, and I'll draw a red wave. And at first you think, oh, it's the same, but I'll make the red wave have a slightly higher frequency, shorter wavelength, and it messed up. Now let's look at their superposition. Indeed, let's look at their superposition. Their superposition at first is big because they're together. It's still big, and now it's almost as big, but they're not lined up quite as well anymore. And then it keeps kind of fading out a little bit as the lineup gets less and less good, and then it's not good at all. But then a little bit later, it's still not good. I didn't do this very well. I did this rather poorly, but it eventually starts coming back. I think I'm better off drawing the superposition without trying to draw the individual waves. I think you follow what I'm saying. I hope you do. Let me draw the superposition of two waves of slightly different frequencies happening at the same time. It's going to go like this. At first they're together, then they're not, and then they're together, and then they're not, and then they're together, and then they're not, and then they're together, and then they're not. Like that. It looks like one of those, echo or electrocardiogram kind of things or something. Notice there's like an envelope of this. If I show the amplitude of it, it does something like this. If this is sound, this is loud, and this is soft, and this is loud, and this is soft, and so forth. So you have this alternating loud, soft thing that really should have been two notes that were just barely different frequency, like and slightly different. Now, if I had someone else here to do this with me, if we were in class, we could sing together, and it would be really irritating. Let me show you on the keyboard. I can do it on keyboard. I'll bring the thing over here. I can see the dog again. Let me show this on the keyboard. Okay. Icona. Okay, we're going to see something on the keyboard right quick. I'm going to play a couple of notes. First of all, let's see. I should have some kind of thank you. I should have some kind of tone that stays on. I'm not sure this is the right one to use. I think a fluty kind of thing, or maybe one of the synth things. Or a sine wave maybe would be best. Oh, go ahead and add it. That's a good one. Okay, listen to this note right here. Listen to this right here. This is a 110 hertz right there. Now, there's a little bit of wobbly in it just because they made it that way. It's just kind of deliberate. That's what I'm going to be talking about. Listen to this note. Both pretty smooth, playing together. That's called beats. Beats are what happens when you have two notes slightly different frequency. If they're more different, they get in and out of sync with each other more frequently, and the beats get more frequent. And I make them even more frequent. And when they get about this frequent, people kind of like it. The beats are so frequent now that you can't hear them individually. Listen again. That's annoying. That's really annoying. That's kind of annoying. Not so annoying, and by the time you get this different, it's almost like, in fact, that's exactly what it's called, a fifth. It's a 3-to-2 ratio. If I play the notes way up higher, the same notes, and play them together, that's pretty grating. But notice those are really faster than those. I haven't explained what the different notes are yet. I'm going to do that at some point. I'll actually teach that. But in any case, this, oh, that's pretty irritating beats. That's what beats are. By the way, if you can use beats in a very useful kind of way, what you can do is you can use them to tune things. I use that to tune guitars all the time. I listen for the beats. When it's making beats, they're out of sync with each other. When you can make the beats go away, you got them in tune. And here's some easy math. The super easy math is that the beat frequency, well, you know what? I'm not even going to write it down quite yet. I'm going to talk about the swing set for a minute. With the swing set, you've got like the two going together like that, okay? But what if one of them's a little more frequent than the other? What if one kid is swinging 20 times per minute and another kid is swinging 23 times per minute? My question for you then is, how many times per minute do they get married? How many cycles of getting married, divorced, and married again do the kids go through if one swings 20 times a minute and one swings 23 times a minute? Well, the answer is, let's see if you get it, 3. How did you get 3, you say? Well, I could do it other ways. I could say, what if you run 20 laps around the track in an hour and your friend runs, they're faster than you, 23 laps around the track in an hour? How many times do they humiliate you by passing you, laughing you, say hi, and you go, oh, because you're beating me. Some guy blew by me the other day on Main Street. It was about my age too. Anyway, never mind. So if they are running 23 laps every hour and you're running 20 laps every hour, they'll pass you 3 times an hour. How'd you get that number? Super simple. You subtract. The beat frequency equals like the high frequency minus the low frequency. That's all you got to do. It's called subtracting. For instance, if I play 2 notes and one of them is, say, 110 hertz and the other one is 103 hertz, you'll get 7 obnoxious loudnesses every second. Blah, 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 like that. I don't know if that's 7 a second, but that's what it is. Now, I'm going to talk more about musical more later. I might throw that in another video. But for now, just know there's this thing called beats. Last thing for this video, and I say we're up to 35 minutes. This is a long one, sorry. Next thing is the thing called resonance. I wish I had brought something home. I didn't bring it. Oh, well. I'll have to tell you about it. Let's go back to the swing set example. I have granddaughters, the older of which is 4.5, and she now knows how to pump the swing. Hey, Beth, Abby knows how to swing by herself, doesn't she? Yeah. Yes. She knows how to pump, how to pull back on it and do it right so she gets going. But I remember when she was trying to learn, she just didn't get it. She'd like pull and push and just kind of get jerked around like that. And I'd have to come up and push her. How often do you push a kid who wants to go higher and higher on the swing set? The answer is so ridiculously obvious, it's almost insulting to ask the question. Just try to imagine somebody, oh, the answer, sure, okay, just in case you didn't get it, you push them just as often as they swing. Just as often as they come back, you push them once every time they come back. You can push them once every other time they come back. It doesn't work quite as well, but at least it doesn't jerk them around. You want to really mess with somebody, they say, hey, mister, can you push me on the swing? That's creepy. Don't do that at the park. Like, ask strangers to push you on the swing set. That doesn't go well these days, I think. But in any case, like you want to push your own flesh and blood, on the swing set. What if you went up to him and just started going, like that, and the poor kid's just getting jerked around? Or if you push them with even a slightly different frequency than what they're swinging, it still doesn't work well. They don't get going very well. What frequency do you use? The same frequency they swing at. This is called, and I erased it, it's called resonance. And a way to define resonance is I could say the driving frequency equals the natural frequency. I had a good example I could have used. Let me just describe it really fast. I like to do this thing where I take a glass graduated cylinder, put some water in it, and I can blow across the top. It acts like a flute. It goes hoo, 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 like that, and I get it where it'll do that. And by the way, if I put less water in it, it makes a lower note, like hoo, hoo, hoo. Okay, then I get a tuning fork that you hit, and it makes a sound. And it turns out, if I get the tuning fork to have the same frequency as the sound it likes to make, it gets really loud when I hold the tuning fork over. It's like pushing a kid on a swing set. It really gets going. It's resonance. Whereas if I use a slightly different, or especially a very different frequency, it's lame. It doesn't make much sound. I would take my thing here, and I'd do one that's not the right note, and I'd pass it over. If I do it just the right note, get it matched up, it goes, okay, something like that. And so the phenomenon of resonance is when you match up with something frequency-wise, you can really get it going, like swing sets and lots of other things like tuning a radio. There's so many resonance things in the world. I have now defined my words, and I'll shut up and leave that for another time and post some questions about what I said. Bye.